Carbon family. Group 14 is very familiarly known as carbon family. Group 14 elements are carbon, silicon, germanium, tin, lead. Carbon symbol is C, silicon Si, germanium Ge, tin Sn, and lead Pb. Carbon having an atomic number 6. Carbon atomic number is 6. Silicon atomic number is 14, and germanium atomic number is 32, and tin atomic number Sn is 50, and lead Pb, its atomic number is 82, and the flerovium and radioactive sample will be having an atomic number 114. So these are group 14 carbon family. In that group 14, we need to study about in detail in this the elements of carbon and silicon. Move the property, reactivities of all this group, general property and reactivity of all this group. Okay, and this group 14, out of that we need to concentrate the first two. The general electronic configuration of this group is Ns2 Np2. So after 13, the next one. Compared to group 13 and group 14, so one valence electron will be increasing. Ns2, Np1 to Np2. The electron as is added to the same shell, hence atomic size decreases across the period. Compared to group 13, the atomic size will be decreases. Covalent radii will be smaller than that of the earlier one, group 13. Okay, and in this carbon will be having a general formula, means not only carbon, all the group 14 having a general formula, Ns2, Np2. Just an example of carbon 6. Its electronic configuration is 1s2. 1s2 can be written as helium, right? So helium, after that 2s2, 2p2. Outermost electron 2 plus 2 is equal to 4. General valency of group 14 is plus 4. Plus 4 is the general valency. Okay, and this not a fixed valency. Valency will be varies. We call it as an oxidation number, or a charge possessed by an atom. It's called an oxidation number. An oxidation number will be varies from the plus 4 to plus 2. So plus 4 minus 4 and plus 2 will be the probable oxidation state for the group 14. Okay, and out of this, we need to concentrate on the first two elements of carbon and silicon. So earlier we were discussing about the carbon. Carbon, so it will be occurs in crystalline as well as amorphous form. Crystalline form as well as amorphous form. In the case of the crystalline, in crystalline form compounds are the graphite and diamond. The carbon will be exist in crystalline as the graphite and diamond. So in the case of the amorphous, so coal, charcoal, carbon, different forms of the carbon only, that is coal, charcoal, and coke, and etc. These are the amorphous form of of carbon, and it occurs in combined state form. It occurs in combined state form, and that is in the form of proteins, carbohydrates, fats, and their form. And this present in hydrocarbons, in the natural gas and the petroleum. Natural gas consisting the carbon major the content, and as well as in petroleum product will be having the carbon and hydrogen that consist of carbon. Okay, so it occurs as exist nature. It will be exist as CO, carbon monoxide, and carbon dioxide in the atmosphere will be exist as CO2 and CO, and it will be occurs in different carbonate forms, that is exists as an oxide. We said that will be impurities, means which will be combined with an oxygen or the carbonates. Oxygen as an oxide, carbon dioxide and carbon monoxide, will be exist as the metal carbonides like calamine or dolomite. Calamine means that is zinc carbonate, ZnCO3, calamine, and magnesium carbonate, MgCO3. That is, we call as mixture of MgCO3, CaCO3 is called dolomite. Dolomite. Okay. Then siderite and many of the different carbonate forms. So carbon will be exist in different carbonates form. Okay. And as like carbon, so most available, the availability of carbon is also more. As like a carbon, silicon is also exist. Silicon is the second most abundant element. Silicon is the second most abundant element, and it is never found in free state. Its availability is roughly 27%. Silicon, second most abundant element, and its availability is 27.7% by the mass in the earth crust, and it's never found in free state, always will be exist in the combined state only, combined state as silicon dioxide, SiO2. Okay, and it will be widely forms as silica. Well, widely forms exist as silica. SiO2 is called silica. Si is silicon. Okay, this is what we call as SiO2. We call as sand or quartz. Sand or quartz, the same of SiO2. Okay, it will be exist in both crystalline as well as amorphous form, both crystalline as well as amorphous form. So this is also used as a semi-precious stone. I said an earlier boron as like semi-precious stone, and the semi-precious stone consisting the silicon, and it will be exist as some other compounds like the feldspar, sodium aluminum silicate, sodium aluminum silicate, NaAl Si3O8, Si3O8. So this is what we call as feldspar. This is what we call the feldspar. So how it will be exist, and also in different other forms it will be exist. And the rest of the compound, germanium, so it will be in very less. So availability of germanium is roughly 1.5 parts per million. 1.5 ppm is very less. So ppm, parts per million, 10 power 1 divided by 10 power 6, very small. And it is and it will be exist, and the tin, germanium is very less, as well as tin also. The availability of tin is that is also less. That will be consisting the natural existence of roughly 2 ppm, 2 parts per million tin. Okay, and which will be exist as SnO2. Tin will be exist as SnO2. SnO2 we called as cassiterite, Cassiterite, cassiterite O. And lead is the availability is roughly 13 parts per million, 13 parts per million ppm, and the main ore of the lead is PBS, we call as galena, PBS or lead sulfide galena. Not only galena, it will be exist in different form also, lead sulfide, lead carbonates, and other forms. This will be the whole the group 14 elements. Okay, so we need to study, we need to concentrate more on this two, carbon and silicon. So we'll see in detail how we saw the electronic configuration. We'll see how atomic radius and how ionization enthalpy, electronegativity, and how physical chemical properties will vary with respect to that group, whole group general property, and particular that. Electronic configuration is Ns2Np2. Carbon is the seventh most abundant element in the earth crust, and availability and the graphite. Okay. Harshita. So that is the existence, how we are studying. So we can compare in the normal temperature with higher temperature and other. So it will be changes with the increase in temperature. The property definitely will changes. Okay, with increase in temperature, all these elements. Okay, how we are comparing the previous without any change in the state of matter, how they'll be exist. Okay, and room temperature or normal temperature, how they'll be exist, based on that will be differentiating. Okay, next, availability, how it will be exist amorphous form as well as crystalline form. So it will be exist in isotopic form 12, 13 and 14, and 12 is the most stable isotope. In the 14 is a radioactive sample, will be having 5770 is. Okay, this will be used as a radio dating technology. Okay, and next, covalent radius. In that, we need to discuss about the property. So in the general property, okay, general property, we need to know about the general property, covalent radius. As like atomic radii and ionic radii. Here, atom radii is okay. What about the ionic radii? Tendency of formation of ions for the first of compound, for the most half of the compound is least. Okay, half of the compound is least. Just a minute. Yeah, welcome back. Sorry for the inconvenience. Tell me. So here we need to discuss about covalent radius. In the case of covalent radius expected to be increased. Covalent radius expected to be increased from carbon to silicon. So from silicon to lead, the small decrease is found. So expected to be increase from carbon to silicon, and after that from the silicon, after the carbon, silicon. The elements are carbon, silicon, germanium, tin, lead. Okay, carbon, silicon, germanium, tin, and lead. From what will be the changes? Carbon to silicon expected to be increased. Then from silicon to lead, after germanium, tin, and lead, its small increase is found. So it will be increases, that small increase. Why? Due to addition of new energy shells. And this each succeeding element, the increase in the covalent radii from silicon to lead is small due to ineffective shielding. Again, the poor shielding. Here, the atomic size, we call this an covalent radii, or atomic size decreases because of the lanthanide contraction. Lanthanide contraction. In the case of the lead, tin after the F block enters, no, then for F14, 5d10 electronic configuration, then atomic radii will be decreases. That is what we call as the lanthanide contraction. Okay. Who is this? Let's keep on disturbing. Okay. Next. Sorry for the inconvenience extremely. Why this? Due to addition of new shell, atomic size should be increases because addition of new shells, electron added to new shell, they expect it to be increased, but this will be decreased because of lanthanide contraction. Means ineffective of the d and f orbital. D orbital, again the poor shielding, and the lanthanide contraction. Lanthanide contraction means if block elements whole that group is called lanthanide contraction. Atomic size electron will be entered to F penultimate shells. When the penultimate shell in lanthanum series we call as lanthanide contraction, and below one more is the actinium series. That's what we call as an actinide contraction. Next, ionization enthalpy. First, ionization enthalpies of the group 14 elements are the higher than that of corresponding group 13. Ionization enthalpy. So again, successive ionization enthalpy obviously increases. Here NS2 NP1 after NP2. So NS2 NP2, the little more the force of attraction. So more force of attraction means one S2 and sp3. So remove, obviously atomic size decreases now, so ionization enthalpy increases. Because effective nuclear charge increases, size of the atom becomes smaller, hence the first ionization enthalpy decreases and moving down the group from carbon to tin. Then decrease is very sharp decrease from carbon to silicon, where there is slight increase in first ionization enthalpy of lead as compared to that of the tin. So ionization enthalpies of the values, carbon is 1086 kilojoules and silicon is 786 kilojoules. So you need to be understand this. Ionization enthalpy decreases, right? Should be decreases, but how the sharp decreases? 1086 kilojoules per mole to and 786 kilojoules per mole from the silicon. Silicon to germanium 761 kilojoules, and after that 708 joule and 715 joules. You need to be noticed that here will be increasing. So sorry, it will be decreasing. Decreases from 1086 to so 1086 joules to so 786 kilojoules. From 780 kilojoules to the 761 kilojoules. Okay, then 708 kilojoules. After that, it will be increases 715 joules. So here there is also electron enter to again F orbital, atomic size increases. Sorry, atomic size decreases, amount of energy needed is more. That's the last one. That is the last one in the case of lead. So here in the case of carbon to silicon, carbon-carbon bond is extremely high, more covalent nature. Carbon-carbon compared to the existence of bond between the delocalizing of the pi electron and pi electron between the carbon, means single bond or multiple bond or triple bond. In the case of carbon-carbon single bond and silicon-silicon single bond, from that all these complete whole group, the carbon-carbon single bond is extremely stable. That is the reason there will be sharp decrease in the ionization enthalpy between carbon and silicon. After that, that slightly decreases till to tin, and after that it will be slight increases because of lanthanide contraction. So ionization enthalpy decreases down the group, right? So ionization enthalpy decreases down the group. So because of effective nuclear charge increases, then down the group beginning, there will be high force of attraction between all this electron nucleus with the electron, especially carbon-carbon bond is extremely stable. Due to that, which will be having high ionization enthalpy. Okay, so ionization enthalpy, so that is in the order of ionization enthalpy. It's carbon greater than silicon, greater than germanium, greater than lead, and greater than tin. So lead and tin, Pb and Sn. So there will be, you need to remember this. Remember the order of ionization enthalpy in group 14: carbon, silicon, germanium. Okay, tin and lead. That is lead and tin. Are you noticing here? Or instead of that, you can write Sn greater than Pb. That is also the correct order. Okay, are you getting? Next, electronegativity. So electronegativity, due to the smaller size of an element, this group will be slight more electronegative than group 13. Comparison with the group 13 is slight more higher. Okay, because of who's this? Harshita. Because of carbon-carbon will be having the more carbon-carbon bond is extremely high. So bond dissociation enthalpy is extremely high. Will be forming the most stable carbon-carbon bond. Carbon-carbon bond is extremely stable. You know that carbon-carbon can exist as diamond or graphite. In the case of diamond, carbon-carbon bond is extremely high, hardest natural known substance. Okay. In the case of graphite, it is the less force of attraction is less, but that is a form of carbon only. But carbon-carbon bond is extremely stable, and even at high temperature, extreme high temperature, the carbon-carbon bond will break. Till to that, the carbon-carbon doesn't react with each other, as well as the bond is highly stable. Okay, so electronegativity in group 14 elements are the smaller in size as compared to group 13 elements. That is why there will be decrease. Why there will be high electronegativity? Because of the decrease in the small size, decrease in the size of the atom. So size of the atom decreases, so ionization enthalpy increases. In that, the elements why the group are slightly more electronegative than group 13, because silicon to lead is almost same, and the same increase in ionization enthalpy from the tin to lead. This is due to the effect of increased nuclear charge outweighs the shielding effect due to the presence of additional 4f and 5d electron. Again, due to the presence of the 4f and 5d, 4f and 5d. So what is the Linus-Pauling electronegative values for this? If you write the electronegative values for the group 14, from carbon 2.5, and for silicon 1.8. Next, for germanium 1.8, for tin 1.8, for lead 1.9. So almost the same electronegativity. Here will be high electronegativity, extremely stable. Now, and almost the same, the electronegativity means slight will increase in that because of the imperfect shielding down the group, as well as presence of d and f orbital. Here, due to the addition of f orbital, the atomic size slight decrease, lanthanide contraction. So ionization enthalpy varies. Apart from that, it is almost constant. Okay. So which will be following general trend. Need not to get worried. Which will be following general trend. Ionization enthalpy. Okay. Next, in the case of the physical properties, we need to study about the physical properties of the group 14. Especially in the physical property, group 14 elements, they are solid. Elements are solid. They are less metallic than the group 13. So group 13 is more metallic. Now the metallic nature slightly decreases and non-metallic nature increases. The melting point and boiling points of group 14 elements are generally high. I'm not saying that specifically, generally will be having high melting point and the boiling points. Okay. Not only that, if we have to know that especially the chemical property, because every day what we are noticing in that in the physical property, what are the things you need to concentrate? From beginning, atomic numbers, we know atomic number. Next, after that, electronic configuration, we'll be knowing an electronic configuration. We studied atomic radius, ionic radius, covalent radius, ionization enthalpy, and electronegativity. And density, one more point we need to say in physical property. So we didn't mention there the density. Density of carbon is 3.51 or 2.2. Next, density of silicon 2.34. Next, density of germanium roughly 5.325, and density of tin 7.267, and lead is 11. So density is increases, general trend is okay. But in the case of, if they given a point 3.25 to 2.34, again the doubt arises why this will be 2.34 greater than less, again means increases. So it will be the order like this: 2.22, 2.34, 3.35, 7, 11. Density increases. This is first one with respect to diamond, and second one with respect to graphite. So in diamond, there will be hard, means all the electrons are involving in a bonding, complete closed structure. Then the density is more, 3.51 in the case of carbon. So density increases down the group. Okay, but in the case of the diamond, means in carbon, the diamond will be having the high density 3.51, and compared to the graphite will be having 2.2. In case of the given, if the given usually represented the carbon density, that is 3.51 itself, 3.5 itself. If the 3.5, that should be a diamond, will be having high density, and if they represented 2.2, then it is graphite. Okay, so that is in the density. And the melting point, if you consider the melting point also, carbon will be having extremely high melting point, that is 4,300, roughly 4,300, 4,000 exactly 4,300. Please pick up the call. 3,473. If we take an exact roughly 4,300, and in the silicon 1,693. Or you will be noticing, then it will be decreases 1,218, 1,218. Then it will be decreases tin is 505, then it is almost 600. Slight increases, you know that at an contraction, atomic size decrease. But this will be follows general trend. But the drastic melting point, sharp melting point decreases from 4,000 to 4,300 to 1,600 or 1,700. Again, because of carbon-carbon stable bonding. Carbon-carbon stable bonding. You need to know this. Melting point is also follows. And melting point decreases down the group because in force of attraction decreases. Metallic nature, non-metallic nature to metallic nature increases. And this group will be having the carbon. Carbon is purely a non-metal, and silicon and metallic nature, non-metallic nature slightly started to decrease. Silicon and germanium or metalloid, very familiarly will use in physics as semiconductors. And in the case of tin and after germanium, tin, Sn and Pb are the metals. So metallic nature increases down the group, non-metal carbon to a metalloid of silicon and germanium, and metals of tin and lead. Okay, so here non-metallic nature, more of the sharing of electron between carbon and carbon, the strong covalent bond, the stable bond between carbon and carbon, hence it will be having high melting point, 4,300 Kelvin. Okay, so these are the properties. In the physical property, all the group 14 are solid. If you consider generally, all these are solid. And in the case of group 13, will be shown a special property is the catenation property. Catenation is will be specifically will use for carbon catenation. Carbon can links with a carbon, can able to form a long chain. That process is known as catenation. Okay, generally what we studied. But not only this carbon, whole group 14 can able to form the long chain structure, means can able to form a polymeric structure like carbon, carbon, silicon, 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 can able to form long chain. and such a way can able to form germanium, tin, and lead. But carbon is extremely stable even at high temperature. So this compound will be exist. This compound will be exist. But in the case of silicon and silicon, with increase in temperature, the bond will break so soon. So that room temperature, then below room temperature and below, this silicon bond will be noticed. With increase in temperature, the bond will be break. So non-metallic nature turns into a metallic nature. So at room temperature, silicon act as insulator. With increase in after moderate temperature, with increase in room temperature onwards, then act as the conductor. So this is what we studied as semiconducting property. So metalloids, silicon and germanium are metalloids. Okay, the order of catenation will be seen in the exceptional behavior we call as an anomalous property. So carbon, silicon, germanium will shows germanium tin almost shows catenation property, but lead will be having a pure ionic nature, doesn't shows catenation property. Okay, so next chemical properties. And the chemical properties, here I didn't mention much of this except oxidation number. Okay, in chemical property I didn't mention. So in chemical property, as an important property you need to be, but we know that most of the chemical property is very familiar to us. Okay, because already you studied many of the chemical reactions. You studied water gas reaction, you know carbon dioxide, you know carbon tetrachloride, you know silicic acid, SiClO4 and SiOH 4 times. Those are all already studied. Just will recall which are the types of reaction we noticed and how it will be. Okay, so first in oxidation number. In the case of oxidation number, group 14 shows an +4 oxidation state. Familiar oxidation, general oxidation state is +4, right? In the case of the first element of group 14 completely shows +4 as well as +2 oxidation state. Due to inert pair effect, NH2 electrons are not involving down the group, are not involving. If it's not involving in a chemical bonding, then +2 is more favorable. Okay, lead, last one, lead shows in +2 oxidation state, least existing of the +4 oxidation state. And +4 oxidation state, which of the element shows +4 oxidation state? Those are an oxidizing agents. Okay, and +4 to +2, I need not to explain more because in group 13 itself, you know that how it will be varies in +3 and +1 oxidation state, as like in this group also. Okay, and C4 do not exist as C4 plus do not exist as C4 plus. The sharing of electron instead of ionic nature, then the sharing of electron is more because of high ionization enthalpy and small size. Due to small size and high ionization enthalpy, existence of C4 plus is difficult. Okay, carbon can be exist C22 minus or C4 minus, C22 minus or C4 minus, and this can easily combines with the carbon and all. Carbon can easily combines with other elements, can exist as so earlier we studied about carbide, Be2C, beryllium carbide, or calcium carbide, CaC2, Al4C3, aluminum carbide, or etc. Okay, and silicon also shows the trend similar to that of carbon. Which one, Harshita? What you are saying? I didn't see. D orbital. D orbital. Carbon doesn't consist D orbital. So absence. So covalency is restricted to 4 itself. Carbon cannot show covalency more than 4. Reason behind in it is absence of d orbital. Here also the d orbital, Raman's property as it is, absence of d orbital. Okay, so cannot beyond 4, can't show is can't extend its covalency beyond 4. Silicon also shows the same trend as like the carbon. Okay, so in +2 and +4, which are the most favorable oxidation state, how they'll be exist as +2 and +4. So you need to remember, so +4 silicon and carbon is almost same, no, doesn't exist, will be exist as so 4 oxidation, that too minus, or will be exist as dimers, not C2 or Si2 will be exist. Yes, sir. Apart from that can show because will be consist D and Fr by 2. But in the case of silicon, what happened? Carbon can't show absence of d electron. But in the case of silicon will be, so force of attraction between them is very weak. Okay, so they can't hold that, means they can't exist. But rest of other compound can show variable oxidation state, but more similarities down the group between carbon and as well as silicon. Between carbon and silicon, there will be more of similarities. Similarities because almost having the same atomic size, no? Yes. Next, are you getting? Next, germanium. So sorry, in +2 and +4 oxidation state, no, we're saying germanium and tin and lead. So germanium, tin and lead, the order Ge2 plus is less than Sn2 plus is less than Pb2 plus. This is Pb2 plus. So the order you need to remember how it will be +4 and +2 oxidation state. Germanium 2 plus is less than Sn2 plus is less than Pb2 plus. +2 oxidation state, right? Predominant down. And in the case of +4, germanium G4 plus will be greater than Sn4 plus and will be greater than